Welcome to Notes on 11.3. Today we're talking about titration, and we're also going to be talking about acid-base neutralization. Today's kind of a sad day, and I'll tell you why in a little bit. Before we do that, here's what I want to do. Quick review. The question is acidic, basic, or neutral. Look at those four substances, look at their pH, and tell me acidic, basic, or neutral. What are they? Okay, here we go. Here's our time to shine. We've got pHs we know that are less than 7. We know that those are acidic. And if you have a pH greater than 7, you are basic. So that means that coffee and orange juice are going to be considered acids, while eggs and NaOH are both going to be considered bases. Also, if you saw the OH on NaOH, that's a characteristic of a base. So yeah. Today's a sad day because we're going to be talking about titration. Now, titration, if you've heard anything about this class, is probably the most exciting lab we do. We really get in the lab, you get to see how well you can perform a procedure that's pretty complex, but once you learn it, there's kind of a curve to mastery. So it tends to be a lot of fun. We'll talk a little bit more at the end of this lecture here today about what a titration is, what it looks like, what it does. So I'm really bummed because I really enjoyed the titration labs, and unfortunately we won't be able to do those since you probably don't have acids and bases and indicator solutions at your house. Not to say that I do, but anyways, here's what a titration is. It goes by this equation, which is molarity times volume equals molarity times volume. We've seen equations like this before. This is very similar to Boyle's law. PV equals PV, pressure times volume equals pressure times volume. And it's a similar relationship. As your molarity, as your concentration goes up, the amount of volume you need goes down, right? So if you have a super concentrated solution, you don't need a whole lot of volume of it. Now, if you're trying to, if you have a super concentrated solution with a little volume, in order to make that equal with a not very concentrated solution, a dilute solution perhaps, you would need a lot more volume to have the same moles of each. So what we do in a titration is, you'll notice molarity and volume here are in red versus molarity volume are in blue, is we try and equalize the amount of acids and bases. So usually our acid will have one concentration and our base will have a different concentration. So what we have to do is figure out how much acid do we add to neutralize such and such amount of base. And we're going to be just working with strong acids and strong bases. Strong acids and strong bases neutralize each other pretty well. If you have a weak acid or a weak base, it's a lot more complicated. So we're just going to stick to strong versus strong. Strong acids and strong bases. So here's a question. This is very similar to a question you'll see. It says if you have 300 milliliters of a 4 molar, 4 capital M NaOH solution, what volume of 3 molar HCl will be needed to neutralize it? So I'm just going to roll through this one really quickly. Notice these numbers are easy as a way to kind of show you that this math doesn't have to be hard. We're going to take the two numbers in blue, put them on the blue side. We're going to take the number in red, put it on the red side. And then since we're looking for volume in this case is going to be X. We don't know what our volume is, but we know our molarity. And then we know that we've got 4 molar and 300. So you can probably solve this in your head, hopefully. And if you do the math here, you figure out you get pretty much 3x equals 300 times 4. So solving this, we just divide both sides by 3, and we get an answer of x is 400 milliliters. So if you have 300 milliliters of a 4 molar solution, that's the same thing as having 400 milliliters of a 3 molar solution. That should make sense kind of in your head, just intuitively. That's titration. That's all titration is. How we're going to make this more complicated is just the numbers. You'll have more sig figs with your numbers, or you'll have, just numbers that look funkier than 4 and 3. So, be prepared. Moving on to the next slide here. What do we have? Why is it not doing this? There we go. Titration is MV equals MV. We've talked about this already. So here's what's actually happening in a titration reaction. is it's used to determine the concentration of an unknown acid or base by neutralizing it. So we will either know the acid or know the base. For the purposes of most chemistry labs, they are going to have a known base and an unknown acid. That's usually how we work, but you could do it the other way around. We know that if you have an acid and a base, if you neutralize them, you get salt and water. And when you neutralize them, the pH of the base or the acid goes to 7. That's how we know when they're neutralized. So we're going to be doing these things called neutralization reactions, which is you have an acid, you have a base, you're going to get this thing called a salt, and the leftover part is water, H2O. So we're going to spend some time working on how do you exactly write a neutralization reaction. This neutralization reaction is just a specific type of double replacement reaction. So if you guys remember double replacement reactions, hopefully you do. They were fairly straightforward. If not, we're going to delve into those again a little bit. Hopefully the second time around will be better. So, little review. Hope you're excited. Here's a bunch of text that tells you if we have an unknown base, usually we'll use a 0.1 molar HCl solution. And if we're looking for an unknown acid, so the acid's the concentration we don't know, we'll use a 0.1 molar base. So that's just saying these are kind of the standards. I guess saying that, it does change sometimes. Actually, no, I'm tripping. Yeah, these are kind of the standard base or acid solutions we use. So acid to neutralize a base to neutralize an acid is what we're saying here. Okay, on to the next thing here. Next thing we're going to be looking at is acid-base neutralization reaction. So here is an example of an acid-base neutralization reaction. We have HCl plus NaOH. So this is a super nice one because everything's got one. We've got one H, we've got one OH. Fun fact, if you combine H and OH, you'll see here that forms H2O. And then you combine the Na from our base and the Cl from our acid, you get NaCl. So this NaCl is what we call a salt. In this case, NaCl is just regular table salt. Any combination of a metal and a nonmetal is a salt. And then you'll see HOH, that's H2O. You got two H's and one O, H2O. So we'll sometimes write it as HOH, just so you can see that red H comes from the acid and the blue OH comes from the base. Now, some neutralization reactions will be a little bit more tricky, like for example, this bottom one here, H2SO4. What I want you to do is break out that periodic table, it's time. Take a look at the charges. So what is the charge for SO4, for example? And try and solve this equation. Okay, let's take a stab at it. Hopefully, since you notice here you have two H's, you knew that SO4 has a 2 minus. And since you only have one Li, you know that Li is a 1 plus. So that's a nice way that you don't really even have to use the back of your periodic table to solve these. You can just figure them out based on how many H's you have. If you were to have 3 H's here, for example, your ion would be a 3 minus. Or if you had multiple OH's, like 2 or 3, that's whatever the number, the subscript would be here, that's the charge of your metal. So we're going to combine H and OH here to form H2O, and then our salt is going to be Li2SO4. We need 2 Li's here because each Li has a 1 plus charge, so 2 of them gives us 2 plus charge, makes LiSO4 have a total net charge of 0. Because we got 2 1 pluses versus 1 2 minus from our SO4. SO4 has a 2 minus charge. Each Li has a 1 plus. This is not balanced, so it's that time again. We're going to have to go back and balance it. It shouldn't take too much. I think you just need a 2 here next to LiOH, and then a 2 here next to H2O, and then 1s. Yeah, that's balanced. So hopefully you balanced it out. If not, remember balancing. That's a thing. You want the same number of elements, compounds on both sides. So you want to make sure you have 2 OHs on both sides, 2 Li's on both sides, 1 SO4 on both sides, and 2 H's on both sides. Here's another problem. Here now, instead of having a 2 next to the acid, we've got a 2 next to the OH in the bases. So go ahead and try that one out. Hopefully you solved it. Here it's going to be CaCl2 and H2O. And then to balance, once again, it's going to be 2, 1, 2, 1. Just so I have equal numbers of Cl on both sides and equal numbers of those red H's on both sides. Acid-base neutralization reactions. These can be kind of tricky. So hopefully you're confident with double replacement reactions. If not, no worries. We have some practice coming at you. Get excited for that. Here's a neutralization reaction, or I guess you could call it a titration. Stomach acid. You'll see here we got milk of magnesia. That's an antacid. So your stomach acid is mostly, I don't know if you can see it, but it says hydrochloric acid on that bottle there. So if you pour some hydrochloric acid in with your milk of magnesia, it'll change color and neutralize. Fun fact. Equivalence point. This is what we want to reach in a titration. The equivalence point is equal amounts of acid and base in the solution. That's the definition. That's what you want to write down. Here's what it means. Your concentration of your H plus is the same as your concentration of your OH minus. Fun fact, if you have equal numbers of H pluses and OH, that means every H plus can bond with an OH minus. And when they do, they form just regular old water. So a way we can write that without writing concentration of is we put little brackets around a chemical. So in this case, a bracket around an H plus means concentration of H plus. Brackets around OH minus means concentration of OH minus. So that's a fun little shorthand that we'll use more and more often in the future. And then, yeah, that little bracket chemical means it's the chemical's concentration. So you can put anything in here, and brackets around it means concentration of. Fun fact. And then, yeah, like I said, since you have H and OH in equal amounts, that means you're neutral. So your pH is going to be 7, which means neutral. Great. On to the next slide. Here we go. Here we're looking at a ring stand and a titration setup. So here's how this is going to work. Below, okay, so first off, we got a, let me pull this up here. We've got a burette clamp. That's the thing kind of keeping the burette all together. And then we got a ring stand. You've probably seen a ring stand before. I don't know if you've ever used a burette before, so that might be new. And then the little valve thing, that controls the amount of liquid that comes out of the burette. And it's called a stopcock, which is a fun name. But the cool thing about a burette is that it reads the volume from the top is 0 and the bottom is 50. So you'll actually measure stuff by subtraction. So let's say you use up 10 milliliters, you'll go from 0 all the way down to 10, and then you'll know, hey, I used 10 milliliters. But you might not always start right at the 0 mark. Oftentimes you don't want to, so you'll maybe start at 2 milliliters and then go to like 6 milliliters, and then you know, hey, I used 4 milliliters of whatever's in here. Typically, in a typical reaction, here's what this is going to look like. You're trying to figure out the molarity of a acid, and we've got base in the burette up here. So we've got probably 50 milliliters of NaOH at 0.01 molar, which is standard base solution. And what we know is, we know that this acid has phenolphthalein indicator in there. And we know that phenolphthalein indicator changes the color of the liquid from clear to pink. And we know that once this solution here turns pink, we know that we've reached the equivalence point. We know our solution is neutral. We know our concentration of acids and bases are equal, as it says here. And we know that the solution is neutralized. It's got a pH of 7. We know we're done. We've reached the equivalence point. So what we're going to want to do is kind of very slowly add NaOH from the burette into the Erlenmeyer flask. So I'm just going to show you, maybe we're starting at something like 2.03 milliliters. And then, oh, watch this. This is dope. We add in some more base. Did you notice what happened to the thing? It turned pink. I was super proud. Guys, this might be the dopest PowerPoint of 2020. Definitely up for contention for dopest PowerPoint of the Rona. Put me up against anyone. I know. You want to see it again, so I got you. I got you. Here we go. You ready? There it is. And then look, it turns pink. Did you see that? Oh, I'm so good. Anyways, so we started at 2 milliliters, and then we maybe went down to something like 8.46 milliliters. So you can probably figure out then that the total amount of base used in this case is 6.43 milliliters. So we've got 6.43 milliliters used. We know that it's a 0.01 molar solution. We know that we neutralized 10 milliliters of acid. So just doing some quick math here, we can know now exactly what the concentration of HCl is. So why don't you guys take a moment, go ahead and try and figure out what would that concentration be. Okay, so we're trying to figure out what the concentration of this 10 molar HCl is, and I think it is, boom, right there on the screen. That is the concentration of the acid that we're looking for. Hopefully you got that. Hopefully you did a little MA or MAVA equals MBVB to find that out. Cool. Moving on here. This is what a titration should look like. It should almost look clear, just a tint of pink. In fact, some scholars say that this is too dark of a pink. Every year, I've got a couple of kiddos that produce titrations that look like this. Fortunately, none of you guys will fail that epically, just because we won't be doing titrations this year. So this is kind of the sad part of the lesson. This is supposed to be the most fun we have in a chemistry lab. And it doesn't happen this year. Rip in peace, titration run. Anyway, so here's the equivalence point. Here's what it looks like. And this is actually what makes it super, super difficult. So I don't know how good you guys are at reading graphs, but I'm a god at it. You also need to be really good at it for the ACT. So here we go. It turns out that your pH doesn't really change except when it does. That's what this graph is saying. So it's saying here, you could add 48 milliliters of NaOH and your pH would go from 1 to 2. Maybe a little bit higher, maybe like 2.5. But then if you add like an extra 2 milliliters, your pH to get to like 48 to 52 there, so an extra 4 milliliters, your pH is going to go from 2 to 12. So you add 48 milliliters, no change. Then you add an extra 2 milliliters, huge change. That really sucks, because what we want to try and get is we just want to get the lightest of pink right at that equivalence point. So if you add like half a drop too much, sometimes it can go from no color to bright pink, which really sucks. So oftentimes we'll have to do this multiple times just to really get a perfect solution. And then saying, yeah, when titrating, we're going to try and get as close to the equivalence point as possible. And so, yeah, there's a really, really small margin of error, and kids rage a little bit. So at least you won't have to rage, but you won't get the fun satisfaction of actually nailing that light pink color, which is sad. Titration calculations. Here are some more example problems. You can try them if you want. I don't know. We've kind of already gone over it. It's MV equals MV. So here's the setup. Pause it if you'd like. Go ahead and try it. Great. Let's go over the answers here. It looks like, yeah, you just kind of are going to divide these numbers and you get 0.16 molar, at least is what I got. Next slide, we've got a very similar problem here where we're going to do the same thing, titration calculation. Once again, we're given an acid, given a base. You're going to have to know that the KOH is a base and the HNO3 is an acid. We give you milliliters and molarity. Something to watch out for is sometimes if I'm feeling super tricky, I might put one volume in milliliters and another volume in liters. And then you can't compare those two. You have to have them both in liters or both in milliliters, whichever one you prefer. Generally, chemists like to have their volume in liters just because molarity is moles divided by liters. So if you're putting them in milliliters, you're technically not comparing the same thing. But I'm just going to say for the purposes of our class, as long as they're both in the same unit, so they're both in molar, big capital M, or they're both in milliliters, you're good to go. So then solving this problem, Now, since we're finding the molarity of the base, we're going to divide by 40.5. When we do that, we get ourselves an answer, and that answer is 0.773 molar. Hopefully you're feeling confident with the titration calculations. Hopefully you get an idea of what titrations look like with that dope animation. And hopefully you're feeling confident about neutralization reactions. It's a return of double replacement reactions, which were difficult, but a little bit easier because it's always H2O and a salt that are your two products. Great. Thanks, guys. Hope you have a great rest of your day. Take care. I will see you all soon, hopefully.